A European robin weighing less than half an ounce can navigate from Scandinavia to sub-Saharan Africa and back twice a year across thousands of miles, hitting the same locations with pinpoint accuracy, using a compass built from quantum physics happening inside its own retina. Most people know birds migrate. They know that somehow birds find their way across continents season after season with a reliability that rivals modern navigation systems. They assume it's a general instinct, a pull towards south. Maybe they follow coastlines, or track the sun, or navigate by stars. All of those things are partly true. Some birds use star patterns, some track landmarks, some use the sun's position. Researchers have been building a complete picture of bird navigation for decades, and the picture is layered and complex. But one piece of it kept resisting explanation: the magnetic compass. The ability certain birds have to detect Earth's magnetic field and use it as a directional reference even on overcast nights with no stars, no sun, no visual landmarks at all. The ability was documented behaviorally. The mechanism was unknown. When researchers finally looked closely at what was actually creating this sense, they didn't find biology, they found quantum mechanics. The European robin's magnetic compass is not a cluster of magnetic crystals acting like compass needles. It is a light-driven quantum process happening inside the bird's eye, one that exploits quantum entanglement to translate the angle of Earth's magnetic field into a directional signal the brain can read. And it is one of the most genuinely startling things biology has ever confirmed about a living organism. Here is what is happening inside the robin's retina. The eye contains proteins called cryptochromes, specifically a type called cry4. When a photon of light strikes a cryptochrome molecule, it excites an electron into a higher energy state. This creates what physicists call a radical pair, two molecules, each holding an unpaired electron, that are quantum entangled with each other. Their spin states are correlated. The state of one determines the state of the other, instantly, regardless of the distance between them. Earth's magnetic field is extraordinarily weak, too weak to directly influence most chemical reactions by any known classical mechanism. But radical pairs are exquisitely sensitive to magnetic fields at exactly this scale. The direction and local intensity of Earth's field influences which spin state each entangled electron settles into. That spin state determines which chemical reaction follows. Different reactions produce different molecular products. Those products generate different signals sent to the brain. The bird's nervous system receives a magnetic field-dependent chemical signal from light mediated by quantum entanglement that encodes directional information. Researchers believe this may manifest as a visual overlay in the bird's perception, a brightness gradient or spatial pattern superimposed over normal vision, shifting as the bird's head rotates relative to Earth's magnetic field. The robin may literally see the magnetic field, not as a separate sensation it has to consciously interpret, as a feature layered directly into its visual experience of the world. This is the working hypothesis of multiple research groups. It is supported by behavioral evidence, by the anatomical location of cry4 in the retina, and by experiments that would make no sense if the mechanism were anything other than quantum. Here is the evidence that is hardest to argue against. Researchers at the University of Oldenburg found that European robins lose their magnetic compass ability when exposed to weak radio frequency electromagnetic fields, fields roughly comparable in strength to what's emitted by AM radio towers near cities. These fields are far too weak to affect any known classical magnetic sensing mechanism. They would do nothing to compass needles made of magnetite crystals, but they are exactly the right intensity to disrupt radical pair spin chemistry. They create noise in the quantum process. The birds stopped being able to navigate, not from light pollution, not from noise, from radio waves, at intensities we barely register as present. This led to a finding that nobody expected. European robins in urban environments were showing degraded magnetic compass performance, not because of anything visible or audible, because the electromagnetic background noise of modern cities, from AM radio, from wiring, from transformers, was interfering with quantum chemistry happening in their eyes. The birds were getting lost because of radio signals we generate without thinking about, at intensities we don't even monitor. Further support came from studying how cry4 is expressed across the day. In most cryptochrome proteins, expression levels fluctuate with circadian rhythms. Cry4 in the European robin and other migratory species maintains constant, stable expression throughout the day, the behavior you would expect from a protein being used as a dedicated sensory tool, not as part of a clock system. The biology of the molecule lines up with the proposed function. The implications extend well past bird navigation. Quantum coherence in warm, wet, biologically noisy environments was considered nearly impossible by physicists before these studies. Quantum effects were thought to decohere, dissolve into classical behavior so fast at body temperature and in aqueous environments that no biological process could exploit them. The robin's eye appears to maintain quantum coherence long enough for it to influence chemistry, influence neural signaling, and ultimately influence where a bird flies. This opened the field now called quantum biology, the study of quantum mechanical effects operating in living systems. The robin's compass was among its first concrete exhibits. It has since driven investigations into whether quantum effects operate in photosynthesis, in enzyme function, and in other processes we assumed were fully classical. A bird smaller than your fist, navigating by quantum entanglement, being thrown off course by city radio, being studied by physicists trying to understand whether the rules that govern subatomic particles also govern what happens inside living cells. The robin doesn't know any of this. It just turns south when it's time and goes. But we should probably pay more attention to where it's going and what it's using to get there. Share this with someone who needs to know that quantum physics is happening inside a bird right now.